Hi everyone, my name is Sophia Pedigo, and today we're going to be solving a problem in which we have a cylindrical hollow log floating in water. Now we know that the log has some length L, some radius R, and it's filled up to a certain height with water, and we're going to call this top part where there is no water, the length of that H. Now using this information, we're going to see if we can find the density of the log. And in order to do that, we're first going to look at the forces that are acting on the log. Now the log isn't moving, so we know that F equals ma is equal to 0, but there's still the buoyant force and the weight of the log. So we can say that the buoyant force is equal to the mass of the water multiplied by the acceleration due to gravity, and that's going to be equal to the mass of the log, also multiplied by the acceleration due to gravity. Now if we divide both sides by g, that term cancels out, and we could also make a substitution for mass of the water and mass of the log. The mass of the water is going to be equal to the density of the water multiplied by the area that the water takes up inside the log. So we'll call this area CW for the cross-sectional area of the water. And that's going to be equal to the density of the log, what we're trying to solve for, multiplied by the cross-sectional area of the log, which is pi r squared. And both of these terms are going to be multiplied by the whole length of the log. Now, if we divide both sides by the length of the log, that term cancels out. And if we rearrange to solve for the density of the log, we end up with the density of the log is equal to the density of the water multiplied by the cross-sectional area of the water divided by pi r squared. Now, we have the density of the water and we have the radius of the log, but we don't have the cross-sectional area of the log. So we need to find an equation that we can substitute into this in order to solve for the density of the log. So I'll go ahead and write this equation off to the side, and then we can try to see if we can find something to substitute in for the cross-sectional area of the water. Now the cross-sectional area that the water takes up is really going to be equal to the whole cross-sectional area of the log minus the top section of the log where there's just air. That's going to be equal to the cross-sectional area of the water. However, we don't know what this area is, but if instead we look at this cone-like shape and subtract off the bottom of the cone, that's going to give us this top area, which we can subtract from the whole circle and find the cross-sectional area of the water. And as it turns out, we can actually solve for both of these areas, meaning that we can finally solve for the density of the log. And that's what we're going to do now. So I'm going to redraw this circle a bit bigger. So we have this radius going off to the side and this radius going off to the side. And the water is filled up to this point in the log. And we know that this is some height h. And we know that this height here is going to be r minus h. And then we're just going to call this some theta and this angle some theta. So let's see if we can find that area of the cone. And really, this area is just going to be a fraction of the total circle. So we can write that as 2 theta, which is the angle here and the angle here. And we're assuming that that angle is the same, so we're going to multiply it by 2, divided by the total radians in the circle, which is 2 pi, multiplied by the total area of the circle, which is pi r squared. The 2's will cancel out, as will the pi's, and we're just left with theta r squared is equal to this cone-like area. Now the only problem is we're not given theta, but fortunately we can make a substitution using trigonometry. And we know that this angle is going to be equal to the inverse cosine of r minus h over r. And we can substitute this in for theta, leaving us with the area of the cone, which I'm just going to call A sub c, is equal to r squared multiplied by cosine inverse of r minus h over r. Now I'm going to write this equation off to the side, and I'll just label it equation number 2, and we'll say it's a sub c is equal to r squared multiplied by cosine inverse of r minus h over r. Now that we have that cone-like area, we still just want to figure out what this area is. And the way that we're going to get that area is by subtracting the bottom triangle out off of that cone section. So all we need to do now is find what the area of that triangle is. So we know the area of a triangle is 1/2 base times height. And we know that the height, if we just look at this triangle here on the right, we know that that height is r minus h. So we can rewrite this as 1/2 base times r minus h. Now the problem here is we don't actually know what the base is, but we can just label that x, and using the Pythagorean theorem, we can solve for x and get it in terms of r and h and substitute that in for our base. So let's go ahead and do that. Now the Pythagorean theorem just says b squared, a squared plus b squared equals c squared. So we'll say that x squared plus r minus h squared is equal to the hypotenuse, or r squared in this case. Now, if we solve for x, we're going to end up with x equals the square root of r squared minus r minus h squared. Now we can further simplify this just a little bit, and I'll do that over here. And that'll give us x equals the square root of r squared minus r squared minus 2rh plus h squared. Now we need to distribute this negative sign to all of the terms inside the parentheses, and that's going to leave us with the square root of r squared minus r squared. That'll cancel out, plus 2rh minus h squared. Now we can go ahead and substitute that in for the base, which will leave us with 1/2 multiplied by the square root of 2rh minus h squared, and that's going to be multiplied by r minus h. Now notice that I only solved for the area of one triangle, and we need both triangles. So we're going to multiply this whole quantity by 2, and the 2's are going to cancel out because we have this 1/2 in front. So that's going to leave us with the area of the triangle, which I'll call a sub t, is equal to the square root of 2rh minus h squared, and all of that's going to be multiplied by r minus h. Now that we've solved that, I'm going to write that up here with our other equations. So we have the area of the triangle is equal to square root of 2rh minus h squared, all multiplied by r minus h. Now this is great because we set out to find the top section of this cone so we could subtract it from the whole cross-sectional area of the log to get the area that the water takes up, which is exactly what we have. So using that information, we can now plug these two equations and find the area of the water. So I said that the area of the water is going to be equal to the circle minus this top section, and I said that this top section is going to be equal to, I'll call it a sub w, and this top section is going to be equal to this cone shape minus the triangle. So let's go ahead and use this equation because I have the area for the cone and I have the area for the triangle. So this top shape is going to be equal to r squared multiplied by cosine inverse of r minus h over r minus the area of the triangle, which is the square root of 2rh minus h squared, all multiplied by r minus h. Now we have this top section, and we know the area of the circle is just going to be pi r squared. So we can say that the cross-sectional area of the water is equal to pi r squared minus r squared cosine inverse of r minus h over r minus the square root of 2RH minus h squared multiplied by r minus h. And that is going to be the cross-sectional area of the water, which we can now plug into the original equation that we found and use it to find the density of the log. So let's go ahead and rewrite this first equation, and that'll give us the density of the log is equal to the density of the water multiplied by pi r squared minus r squared multiplied by cosine inverse of r minus h over r minus the square root of 2rh minus h squared multiplied by r minus h, and all of that is divided by pi r squared. And that gives us the density of this log, a perfectly cylindrical log that's floating in water, and assuming that we know the radius and this height where there's just air at the top of the log.